So what's the exam? Thursday, a week from today. We have, so exam 2 is Thursday, the 13th. And it covers all the old stuff. And rigid body statics. So if anyone has any questions about rigid body statics problems, I'd be happy to answer those. The next thing we're going to do is go on to centroids. Yep.
So number 12, I guess.
Number 12, yeah. Do you have it with you?
I got it right here if you want it.
Great. There are two ways you could interpret the way this question is asked. Either one is fine with me. It looks something like this. There's a ball and socket joint over here. And then there's a cable that goes to a pulley. And then that pulley is attached to the wall there and there. And there's a force applied at the center, just straight down, with a magnitude of F. And we have to figure out what the reactions are in terms of this parameter F. So you could interpret this two ways. One, you could just calculate the tension in that cable there, or two, you could calculate the tension in that cable there and the big cable. If you only did one or the other, that's fine with me. Yeah.
Just out of curiosity, would it be fine if you calculated all the forces in terms of tension as well?
In terms of tension. That's not the way that it's meant to be interpreted, but I could give a little wiggle room on this because I probably should have clarified better. But
yeah, because it doesn't say either way.
Yeah, the idea is that we're trying to figure out how those reaction loads vary as F varies.
Okay.
We're treating F as if it's a numeric value, but we're going to come up with these reaction loads as a function of F.
Okay.
I'm going to choose the about point here. And so if we just express, let me label these, they called this A. The end B. Over here, C on the wall where the cable attaches. The other cable attachment point D, and then the pulley E. And since we're going to make the about point at A, we'll choose that as the origin, express all these points as in this coordinate system at A. And if we have the coordinates of all these points at A, then those coordinates are the row vectors for those forces. Okay. So let's first just come up with the coordinates of those points. So A is 0, 0. B is, and I'm going to do this all in feet. So B is straight along the x-axis. I'm going to use a coordinate system like this. X-axis that way, Y that way. Okay. Yes, they give this one. Oh, it's different than this, isn't it? Okay. So X is this way, Y is this way, Z is this way. So the coordinates of B, it's 10 feet along the y-axis then, so that's, oh, and this is in 3D, so I need another 0 here. B is at the point 0, 10, 0. C is in the negative x 4 feet. The 0y and then positive z 5 feet. D is positive 4, 0, and then positive 5. And then E, we don't know that yet. We'll have to come up with that. Okay, so how are we going to come up with that point E? Let's take a side view in the YZ plane. This is the wall. This is the cable, and down here is the pulley. And we know that this distance is 2 feet. This distance here is 10 feet. This distance is 5 feet. And so based on similar triangles, this big outer triangle is a similar triangle to this smaller one. So we know this height has to be half of 2, so that has to be 1. If you didn't see it that way, you could. What?
I just did like the tangent to get the angle.
Yeah,
to get the
that's
correct
fine.
angle to
I mean,
the-
it's just one more step. Use tangent to get the angle, and then use sine. That's what I did the first time, and then someone pointed out. Yeah, those ratios are always the same in similar triangles. Okay, so now we can calculate that point E. We know it's 10 feet along Y to get there. Okay, so E. X is 0 for E. Y, it's 10 feet minus 2 feet. Backtrack 2 feet. So positive 8Y. And then for Z, it's up 1 foot. So there. I didn't draw out the dimensions, so it's a little hard to follow my thinking on that, but drawing those dimensions is so hard. But anyone have any questions about those coordinates or how we're going to use these?
If you end up having the pulley and that tension there, as part of your two by diagram, or I guess opposite, sorry. If you end up having that whole cable system with tension
Mm-hmm.
from point B, do you even use point E?
Yes. Yep. I'll do it both ways.
For free body diagram, do we have to include the pulleys over there? With, like, you know what I mean? Like, put it inside the free body diagram, or should we just include the beam only?
I'll do it both ways, and yep, we'll see how both of those would work. Okay, so the first approach, I'm going to isolate the beam only. So a free body diagram looks like this. There's a force down of F. At the ball and socket joint, there's a full force vector of unknowns. I'll call that R. And then at the end, there's a single tension T. So the row vector, since we put our origin at the about point, the row vector at each of these locations is just the coordinates. So for the force at A, the row vector is 0. The force vector is Rx, Ry, Rz, and there's no moment. For the downward force F, I didn't give coordinates for that, but that's 5 feet along the y-axis, so the row vector is 0, 5, 0. The force vector is 0, 0, negative F. And so the moment is negative 5F, 0, 0. And then the third one acts at that point B. The coordinates of B is the row vector, so that's 0, 10, 0. And now we need the force vector. Yeah, right. We'll use the unit vector to find that force vector. So a vector that's in the right direction is we could subtract, it's E minus B. So 0, 8, 1 minus 0, 10, 0. So you get 0, negative 2, positive 1. And then a unit vector in that direction is this stuff divided by the square root of 5. Can someone calculate those? Okay. Oh, for y? Okay. And so the force vector applied by that force T is 0, negative 0.894t, positive 0.447t. Yep.
If you are getting a vector like this, whether it be through angles or whatever, and you can see geometrically that the signs are wrong, can you just change those signs? Since it's a unit vector, you know it'll have the same magnitude, but your signs are messed up.
How did your, like you do the calculation and something went wrong in the calculation?
I'm trying to think about this. Say we isolated the pulley too,
Yep.
and you had one T that was going this way, one that was
Yeah.
going that way, and you add, say, negative X on both, but
Okay.
you know the
Yeah.
numbers that should be there. Can you just
Well,
write
I mean, I think if you're doing it one way, and I think the way to think about that is that's a sanity check on your calculation.
Okay.
That tells you something went wrong, so go back to the calculation. I think that's a safer way to do it. You know what I mean? You know a mistake happened somewhere, go back and find it.
Okay.
You know, that's a really important thing to do at each step. Like, what do I know that can give me confidence or concern about my answer? Okay, so the moment is 4.47t00. So Newton's second law says Rx, Ry, Rz plus 0, 0, negative f plus 0, negative 0.894 t, 0.447 t is equal to zeros. And the moment equation says negative 5f plus 4.47t is equal to zeros. So we have 4 variables. Remember, this f is a parameter, so that's going to be in our answer. And we have 4 useful equations. These 2 don't help. So the first equation says Rx, we have 1, everything else is 0. The second one says, of course, that just says that Rx is equal to 0. I usually just put it in the matrix anyways and just let it all work out. Ry's, we have 1 in the second equation. T's, we have negative 0.894. And then here's the one where we're going to use this parameter f. So the way that works is RZ's we have 1, T's we have 0.447, and our constant, we're treating this f like it's a number, so that moves over the other side, and that's positive f. And then the last one says T's we have 4.47 and the constant is 5f. And actually this is one, well, okay, so a couple things to say about this. This one is pretty easy to solve by substitution. If your calculator doesn't do reduced row echelon form for variables, and I don't remember which ones do and which ones don't. TI-89s, you can just plug this in as a variable f, and it'll give you the answers in terms of f. So you don't have to worry about it. But if you have a calculator that won't do that, This fourth equation lets you calculate t in terms of f, plug that in, boo, boo, boo.
That's what I was going to ask about.
Yeah. Any other questions about that one? Yep.
How do you know F is a constant?
Just because it's given. Okay, so let's do it the other way. What did I call this? First approach. Okay, here's the second approach. So we're going to isolate the beam, the short cable, and the pulley. So a free body diagram looks like this. Nope. Okay, so now we're also including the short bit of cable on the end, and we're including the pulley. The ball and socket joint still applies an unknown force vector R, and we still have a downward force F. Now that what we called the cable force T in the last free body diagram is internal, but now the external loads are here and here. And I'll call those T2 just because they're different than the one we called T before. But it's a single cable that's going through this pulley, so those two have to be the same. And so now we have 4 variables like we did before. One of them is just representing a different thing. And we're going to come up with 4 equations. Okay, so the force R acts at the origin, so no row vector. The force is Rx, Ry, Rz, so there's no moment. Then the force F acts at, what direction is that? 0, 5, 0. And the force vector is 0, 0, negative F. And so the moment is negative 5F, 0, 0. And now we have 2 force vectors, even though they both use the same variable. So first I'll do the one that goes to the point C. So a vector in the direction from E to C, from the pulley to the point C, is C minus E. And C we have up here, negative 4, 0, 5. And E is 0, 8, 1. Negative 4, 0, 5 minus 0, 8, 1. So that's negative 4, negative 8, positive 4. And so unit vector in that direction, would that be 0.408?
Yes.
0.8. Okay. negative 0.408, negative 0.816, positive 0.408. And so that's acting at E. So that's 0, 8, 1. And the force vector is negative 0.408 T2, negative 0.816 T2, positive 0.408 T2. And then the cross product is complicated. Can someone calculate that? Punch it into a calculator. Okay, T2. What's the second one? 0.408. Okay, thanks. Anyone get anything different?
I got negative for the y component and positive for the z.
Okay. Negative for y, positive for z. Okay, and then the D one. Well, you guys got the same thing, so we'll go with that. Okay. Oh, okay, for D. So for D, yep.
For D, would you even have to calculate the unit vector? Because you know they're at the same points on the relative axis.
Mm-hmm.
So those magnitudes would still be the same.
Yes.
It would just be the sign of x that would change.
Yes, that's exactly right. The force at D is applied at E again, so the row vector is 0, 8, 1. And so 0.408 T2, negative 0.816 T2, positive 0.408 T2, and then what changes with that moment?
That one is negative z positive y.
Negative z positive y and positive x.
Yep, same values though.
And I'm keeping, different numbers of significant figures everywhere just to show my contempt for the rules of math. Okay, so Newton's second law says Rx, Ry, Rz plus 0, 0, negative f plus negative 0.408 T2, negative 0.816 T2, positive 0.408 T2, plus positive 0.408 T2, negative 0.816 T2, positive 0.408 T2. And then the moment equation, negative 5F00 plus, I'm not going to remember that. So 4.08 T2. This one was 0.408 T2. This one was 3.264 T2. And what were the signs on these? I got it. Positive, negative, positive. And then the other one is the same, just positive, positive, negative. We have three good equations from Newton's second law. This first equation is good from the rotational equation, but equations 2 and 3, we have positives and negatives that cancel out, and so we end up with the same thing we had before, 4 equations for 4 unknowns. When you get those answers, if we did it both of the two ways and we did everything right, we know that R has to be the same, but that T2 can be different from T. Any questions about that one? Yeah. So the variables are R, X, Y, and Z, and then T2. And you do it all in terms of F. Any other questions on that one? Yep.
Oh, never mind.
Any other problems you'd like to go through? Yes. 10, yeah. Rx? Oh, yeah, you're right. Rx is equal to 0 again. Yep. Yeah, these two cancel. You're right about that. So in the first one, remember we saw that too, that Rx was equal to 0, and it looks like it's equal to 0 again. Okay, so 10. I would prefer to make them shorter, yeah. Okay. I mean, I don't know if I'd say 100%. Like, sometimes I'll do tests that are just one problem or whatever, and that's just how it is. But I'd prefer to do fewer problems, more problems, less time for each. Okay. Well, I'm doing a free body diagram here. Let me sort of draw a picture first. So that's a ball and socket joint there at D. There's a downward force of 140 pounds there. there's a cable going over to the wall there, and then this goes up to the wall here. The ball and socket joint location is D. This pulley is C. This point is A. E. The other pulley is F. And then the connections at the wall are H, I, and G. And we're given a coordinate system with the x-axis this way, the y-axis this way, and the z-axis this way. And so again, if we have our about point and our origin coincide, then all of the row vectors are just the coordinates of these points where the forces are applied. So let's just calculate these locations. So A is 140 inches in the x direction.
Worth noting it asks specifically what side units. We'll have to calculate that when we
Oh, okay. Let's do it in these, and then you can convert at the end.
mentioning it.
Yeah, thanks. Yep. I'm saying let's do it at the end so I can weasel out of doing it at the end, and then the point C is at 72x 0, 0. D is the origin. E is 120x and then 10 positive z. F is 120x and negative 10z. G is 136z. H is negative 100z. And I is 44.8y. So now free body diagram. Okay, so I think the easiest way to do it is to include this little stretch of cable in your free body. You don't have to do it this way, but it makes the forces that this part of the cable applies to the pulley internal, and so you don't have to deal with those. We have a ball and socket joint here. We have a force of 140 pounds here. We have a cable force, I'll call that T1 there. And then the other cable, we'll call its tension T2, applies a force there. and a force there.
You have to do 3 force vectors, 3 unit vectors to solve for that.
Yeah, we'll have to do unit vectors for all 3 of those. Yep.
When you get to it, do you use T1 or T2 as through angular methods?
No, I would never do that in 3D. That's the answer to that. Always do it with points in 3D. It's just unnecessarily difficult. I wouldn't even, off the top of my head, I wouldn't even really know how to approach it. I think I would do it with a whole bunch of rotation matrices and think, but it would be a nightmare. So in 3D, you always want to just find the coordinates of the beginning and end points and calculate your unit vectors that way. Yep.
So it looks whereas there's tension, we need to use unit vector to find the force vector. Is it always like that, or?
Yeah, with cables, it's always like that. And with normal forces, too, I guess.
Oh, no, okay.
Okay, so the force R, that's at the origin. The force vectors Rx, Ry, Rz. So the moment is 0. The next one, the 140, that is at the point 140, 0, 0. And the force is 0, negative 140, that's in pounds, 0. One thing that is easy to mix up with these is, and so try not to make the mistake of confusing what's going on with the forces with what's going on with the row vectors. These row vectors are all like distance measurements, length measurements, displacements. These are all units of force. So it makes it, so don't confuse these two 140s. Those are totally different things. I don't know why this problem has a 140 for force and for length, but and if you take that cross product, what's 140 squared? 19600, and that's negative. Okay, so now we have to do the cables. So first I'll do that cable that has the force T1. A vector in the right direction we can get from taking G minus E. So that's the vector shown here. So that's 0, 0, 136. Minus 120, 0, 10. So negative 120, 0, positive 126. And then a unit vector in that direction. Can someone calculate that? Okay. Okay, so this force is acting at E. So the row vector is 120, 0, 10. And the force is this times T1, negative 0.69 T1, 0, positive 0.72 T1. And the cross product, can someone do that? 120 times blah, blah, blah.
0, negative 93.3
Times T1. Oh, not the 1
Yeah,
or the 2. I just made that up. Okay. And now we'll go to the T2 force that's pointing towards I. So the vector in the right direction is I minus C. The coordinates of I are 0, 44.80. The coordinates of C, 7200. So that's negative 72, 44.80. And then a unit vector in that direction, what do you get? Okay. Okay, so this force acts at the point 7200, and the force vector is negative 0.85 T2, 0.53 T2, 0. What do you get for a cross product? 38.16 T2. And then the last force is towards H. So the vector in the right direction is H minus F. Zero, zero, negative 100. Zero, zero, negative 100. Minus, I forgot. 120, 0, negative 10. So negative 120, 0, negative 90. And what's the unit vector? Okay, so that's acting at the point F. So the row vector is 120, 0, negative 10. The force is negative 0.8 T2, 0, negative 0.6 T2. And what's the cross product? Okay, so for variables, we have 1, 2, 3, 4, 5. And every equation is useful except for the x component of the moment equation. Which says that there is nothing there's nothing keeping this from infinitesimal rotations about the long axis. So you get a system of 5 equations for 5 unknowns, get the answer, then you're in pounds, convert to newtons. Yep.
You said earlier that you would have to use rotation matrices if you were to do something like that in 3D. But since all of these vectors only contain two components in 3D, couldn't you just do the same thing on that 2D plane in 3D?
None of them have...
None of them have more than 2 components, i.e. from C to I, that's just X and Y. From E to G, that's just X and Z.
Maybe you're right. Here's...
I get that you can
Yeah.
do it normally,
Yeah.
but
Yeah, you might be right. It doesn't. I don't see it off the top of my head how you would do that easily. And in 3D, I think you'll be happy if you always just do it by points.
okay.
Any other questions about this one? Any other problems you'd like to see? Whose was this? Yep.
Do we have a few test tables from here on out? Is that kind of how we solve most of these?
I'm going to write, I'm going to always write it out like this, pretty much always. We'll get to some stuff where I won't. Whenever we're doing rigid body, so it doesn't help with particle stuff, because the whole point of it is that it lets you organize your forces, well, mostly your moments, makes it easy to calculate the moments. So when you're doing particle statics, there's no moments.
So, like, if I wanted to make this in Excel,
Yeah.
but I could check
Oh, yeah. That's a good idea. It's a really good idea.
and use it for the rest of the
That's what you should do, yeah.
There's one number that about point is not at the origin. I think number 5 is similar, but did it in extra factor form.
Well, you can always put your about point anywhere you want. But you mean in my solution?
Oh no, not the solution. It's because like if you look at number 5, there's thing center of mass.
Oh, yeah, right. Yeah, that's the one with the sort of J-shaped, funny shaped thing. Yeah. Yeah, so you could do it, you could write it out using the, so the row vector is always equal to the coordinates where the point, where the force is applied, minus the coordinates of the about point. So you could always calculate the row vector that
Even
way.
if they give us the origin, like if they give us the origin at the about point, it's not at the origin.
Yeah, so if you put your origin at the about point, A is 0, so P is just equal to rho. If, for some reason, it's hard to put the origin at the about point, like in this example, then just do this subtraction. Whatever the coordinates of the about point are, you just have to do this subtraction. That's why I talked briefly about this longer, the one with the mnemonic device, pancake artist row 4 marzipan. So in that example, you could write out the coordinates where the force is applied, write out the coordinates of the about point, subtract, and do it. If you put the origin at the about point, then the about point is all equal to 0, and everything in P is just equal to rho, and then there's no reason to use these other 2 columns.
For this number, can you put the origin at the about point?
You're right, it's sort of difficult in that one. You'd have to go all the way through. It wouldn't be worth the effort. So you're better off just calculating rho for each one using this definition. But this, you can think of this as the definition of the row vector. Yes? That was this cable here. And that's the same cable as this one. And we called that one T2. Did I? Is that what I did, or? So it should be T2. Yeah. Any other questions about? Yeah.
So generally, every time you see a pulley, the tension rod is going to be this. The tension on the same string and the pulley system is going to be the same.
Yes.
And then
If
yeah.
unless you're given extra information, like, so it's not true if the cable has mass. It's not true if the pulley has mass and things are moving. So in our case, that I guess that wouldn't matter. And it's not true if the pulley has friction. But if it's just drawn in a problem like this, those assumptions are always made. Those would be specifically mentioned if any of those things were present. Yep.
Would it be true if you had a mass between the two pulleys? I.e., if you scroll up for a second.
Well,
As in, if you had a mass between those two tensions, would that
right.
change it?
It depends if that mass is on a acts as a pulley, you know, like if you have a cable and a mass like this, it's going through a pulley there, and so the tension is the same all the way along it. If it's not like that, then you have a pulley, you have a cable that's doing something other than going through pulleys, and then you have to treat it differently.
Okay.
So the tension is the same along a cable if all it touches are pulleys
Okay.
along
It's
its
not
path.
possible for that mass to be anywhere other than the center if it's going through a pulley? Would that be true?
No, that's not true.
Because if that mass is being held up by a pulley, it should just, in theory, go to the center, shouldn't it?
If that mass is loose, I'm not sure about that.
Okay.
I'd have to think about that.
Anyways,
Yeah.
correct.
Any other question? Yeah.
I'm trying to look through this homework and see what the point of it was, so that I can sort of test.
Yeah.
Try to get all the good stuff. So also with the F, if it's a constant, or if there's an F value and it's like the what is the magnitude of the force,
Mhm.
you just treat it like a constant.
Yes.
Okay. And then the last thing I was thinking that was weird in here was the only time that you change the free body diagram forces. So like we've had many examples where something you just look at it, you know intuitively it can't move, but we've always done all the forces. But the only scenario in which you would modify your forces depending on the type of loads is if you have two of the
Yes.
neutral.
That's exactly right.
Okay. That's the only time in which you would just
The only time.
and say, wait a minute.
Exactly. That's the only time. Yep. Yes.
So for 3D joint, but joint category 1 and 2, we see like how I notice if it's 3G, it can look different. How I notice if it's like frictionless contact or.
It'll tell you. That's the only way. Yeah. They don't,
Like.
so it'll tell you whether it's a wheel or a.
Oh, it will tell,
Yeah.
okay. And do we treat it same as 2D, like same rules? It will be perpendicular to the surface of.
Yes.
Yeah,
Yep.
okay.
Yes.
I think questions 9 through 15 are a little bit complex. Are we going to have separations?
You should be able to do all that stuff. Like one thing I can do on the test is I can sort of break problems up, like give you some of the information so that, or say derive the equations but don't solve it, that kind of thing. So you should be able to do all of the things that you need to do in those problems. But you're probably right that I wouldn't have you do problems that long just because I'd like to put more than one or two problems on the test. Mhm.
just regurgitate that information, but like to understand it.
Easier to draw. Okay, so we have a beam at a 45-degree angle. It connects to a pin joint up here. And there's a pin and slot joint here. Where the slot makes an angle of 20 degrees with the vertical. And this angle is 45. So, free body diagram. It has a weight of 850 kilograms times 9.81. I think I remember that's like 8338.5. Let's pretend it's that. Okay. And then the pin joint applies a force vector. Call that R right. And then the pin and slot joint applies a force perpendicular to the slot. So there's a force vector. I'll call it R left. Nope, and that doesn't have a vector symbol because that's a known force direction.
So on an exam, would it be fine to draw that dotted line? At least
Yeah, that's fine, yeah.
Nothing else to show that you...
Yes, actually, that would be
Okay.
nice, yes. Okay, so let's put the about point here, and so that's what we'll also call the origin. So the row vector is 0, force vector is RRX, RRY, moment is 0. Then the coordinates where the weight is applied, that's at 2 meters times cosine and sine of 225. So that's negative 1.414, negative 1.414. And the force vector is 0, negative 8338.5. Can someone take that cross product? Okay. And then the coordinates at the lower pin, I think that's negative 2.828, negative 2.828. And now we need to use a unit vector for that force direction. So here's the way it makes sense to me. If the coordinate system is like this, we know that, this slot is 20 degrees from the vertical. So we know a vector pointing this direction.
Oh, okay.
We know what that 20-degree angle is. So so I'm going to draw it like, I'm going to draw a vector like this. And remember, put all these vectors' tails at the origin. So this angle is 20 degrees. And once we get to this vector, we know it's 90 degrees to get to the vector we want. Because this force is perpendicular to that slot. So start at the positive x-axis, negative 90, plus 20 puts us at negative 70, plus 90 puts us at positive 20. And so the unit vector is cosine of 20, sine of 20. And so the force vector is 0.940, that's the cosine of 20 times RL, 0.342 sine of 20 times RL. And then what do you get for that cross product? 1.69 RL. And so now we have 3 equations, 3 unknowns, you can solve.
I just was confused because the way it's perpendicular this way, so the angle would be 70 degrees if it's perpendicular 90 degrees, then 90 minus 20 would be, 70 degrees this way, and then you subtract 270 minus 70, so it would be like 200 degrees.
Well, I started out by drawing exactly the vector that exactly shows the angle that's given in the problem. So does that one make sense?
Yes.
Okay, so to get to that one, you go minus 90 to get to 270 and then backtrack 20. So does it make sense that we're at minus 70 here?
Yes.
And then if you're at minus 70, now we know that this is a 90-degree angle, so minus 70 plus 90 gives us a final angle of plus 20.
The way I draw the vector is wrong because I draw head to tail.
Okay. Yeah.
It gives me the wrong angle.
Okay, but but you did 200. Is that what you said? Oh, I'm sorry. That is fine because I could have. Remember that the force applied by a pin and slot joint can act in either direction. So I could have just as easily, just as correctly drawn that force this way in the free body diagram, and then it would be minus 70 to get there, minus another 90 to get there, which is minus 160, or if you went the other way, that's plus 200. So that's perfect. Yeah. Any other questions? Oh, class is over. Okay, so ask 5 minutes of questions. Aaron, I know you got more. Okay.
I guess I just want to know if you're on the test.
Yeah. That's a hard one for me to answer. I mean, here's what's going to be on the test. Some subset of the very practice problems that I have given you. You know what I mean? If you can, so here's the test. Here's how you know you're ready for the test. If you could look at any of those questions and explain why you made, not just do them, but explain why you made every decision. Because what you don't want to do is like memorize the solutions, But if you could explain like, okay, here this angle is 70 because of this, 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 and this number is negative because of this, this, this. If you understand all the practice problems at that level, then you'll do great on the test.
Are you going to ask us to convert units?
No, I'm not sure why I did that. It was probably very late at night.
Should we remember all zone category, like 3D and 2D?
Yes, those, you do need to remember those, and because I think ideally you don't really remember it. You think of it in terms of what degrees of freedom are restricted and use that to figure out what loads, So yeah, you should be able to do that. But, I was going to say I'll give you all the equations, but there's only 2 equations, and you probably remember those.
Oh, do you want to hold on to this? Do you want this through today? Because I kind of want to use it to study.
Sure, you can keep it.
So I
Yeah.
can turn it in on Thursday.
Yeah, sure. If anybody wants to hold on to homework until the test to help you study, that's fine with me. Or if you want to hold on to it until the test because you've only done half the problems on it, that's fine with me too. Whatever reason you want to hold on to the homework is fine with me because I haven't graded the last one yet.
In rigid body stacks, are we always able to choose the PowerPoint, or is that the